Well, last time, so we constructed free Lagrangians for Dirac, Wall, and Majorana fermions, or spinors, I should say, because we haven't quantized the theory yet. I want to also make a correction to a statement that I made. I said that given the Dirac algebra and our choice of the convention for the mostly minus metric, the fact that we have gamma 0 squares to 1 and gamma I squares to -1, I said that that implied that gamma 0 is Hermitian and gamma I was anti-Hermitian. That is not the case. Kafir and Stavros showed me an example of a matrix which squares to 1 but is not Hermitian. I don't have a proof of this fact, but I suspect that probably given the Dirac algebra and these conditions, that you might be able to show this. But for me, it's much more important to notice that the gamma mu's will enter into constructing physical quantities such as the Hamiltonian, current, charge operator, things that we will be able to measure in experiments, right? So we want those quantities to be Hermitian operators. So having well-defined Hermicity properties of gamma 0 and gamma I will help us construct those quantities. If we didn't have well-defined Hermicity properties of the gamma matrices, we won't be able to construct, for example, currents and things like that. Okay? So that's the motivation, but I will look up, probably some mathematics literature has this from another perspective. If I come across it, I'll let you know. And also vice versa. If you come across such an argument, let me know. So spinors are a lot more complex than scalars, or complicated, I should say. And to understand the properties of spinor fields, when we quantize them, we will need some of their properties. So to do that, today we're going to start with discussing the plane wave solutions to the free Dirac equation. As you know, historically, Dirac found that he had two kinds of solution to the Dirac equation. From the point of view of quantum mechanics, he found the solutions which he called particle solutions and solutions which he called the antiparticle solutions. But we are not looking at for a wave function interpretation of the field psi. So we don't call these solutions like particle and antiparticle solutions, but we call them positive frequency solutions and positive and negative frequency solutions. So the first one is the positive frequency solution. Because according to the picture that Dirac had, he had an idea that somehow the electrons, that vacuum consisted of a sea of electrons, which were at a negative energy. And when an electron was excited from that vacuum, a hole was created, and that hole was by basically what we call a positron. But we don't have those kind of interpretation anymore in the modern in quantum field theory. So let's look at the momentum eigenstates. So let's write our ansatz as this is a 4-component spinner. And a free wave part. And we are going to assume that this is the 0th component is greater than 0. So we now plug this into the Dirac equation in the Weyl basis. So we recall that in the Weyl basis, our gamma matrices look like this. I can write the 4-component spinners as in terms of 2-component spinners. So U1 is the left-handed spinner, U2 is the right-handed spinner, and the derivative operator acting on the exponential gives me this. And then there should be a mass term. And that is equals to 0. The easiest way to solve it is to say that, we are say quantum mechanically it describes some particle. That the particle is actually at rest. So the easiest way is to kind of say that let's take our 4 momentum to be that of a particle at rest. Then it's easy to show that the spinner is given by something like this, where this is normalization. This normalization will allow us to have a relativistically invariant normalization, we shall see. And the zeta are 2-component spinners, constant, which satisfy this. Actually, it's just one. It's not the matrix. Okay? So now, what you can do is that you can say, okay, I'm going to Lorentz boost this solution. And if you Lorentz boost this solution, then you find the spinner U for any arbitrary momentum P. So if you do that, it's a bit of an involved calculation, and I'm going to skip that. You can look at the details in Peskin. You have to parameterize the Lorentz transformation and do some manipulation involving sigma matrices. But the final result is the spinner for some arbitrary momentum is given by this. Then the conjugate spinner is defined in this way, analogous to psi bar. Then it is easy to show that the inner product between a conjugate spinner and a spinner is indeed Lorentz invariant. It's just the mass parameter. So this is a Lorentz invariant normalization. So Zeta is a two-component object. So there it has two linearly independent parts. So we can call these S. We can label them. And then we can choose them to satisfy this orthonormality condition. If you do this, then corresponding to these choices of zeta, we get U bar labeled by S. So you can think of it as a spin label. Although it's not Lorentz invariant, this following relationship is useful in doing some computations. And I code it for the sake of completeness. Once you have done this, you can say, OK, let's look at the negative frequency solutions. So negative and it's customary to call the spinner corresponding to the negative frequency solutions by V. So V of P, e to the power plus I, P dot X, where P is still a positive quantity. This is what the sign difference is what makes it a negative frequency solution. And you can do the same calculation, but there'll be some small changes and derive what the V spinners at some arbitrary momentum is. And there's a minus sign here. Similar to the other case. And therefore, we should get two linearly independent V spinners. There's a minus here. One shouldn't be surprised by the presence of a minus sign because this wasn't supposed to be a positive definite quantity anyway. It's because it's a bar, not dagger here. Similarly, if we were to say what happens if I look at this quantity, which should be positive definite, it is. However, it's not Lorentz invariant. So I know this is a little boring, but in doing computation involving quantum expression of Hamiltonians and stuff like that, you want to find, say, their expression in Fourier space, these relationships will crop up. And that's why I give them to you. The V spinners and the U spinners are orthogonal to each other. They describe they describe different parts of the solution space. So therefore, if you take the inner product between these guys, but at the same momentum, that should be 0. However, if you were to evaluate the analogous quantity here, but with daggers, then that would not be 0. But if you just flip the sign of the 3 momentum, so here by bar under, I mean it's a 3 momentum, then that is 0. And this again comes handy in certain calculation, because in certain calculation you have to, inside the integral sign, you have to set that 3 momentum p to minus of p. And then, this sort of identities come in handy. And then Vs this should be an R. UR of P is similarly 0. Okay? So the last thing that we need about the solutions of the plane wave solutions of the free Dirac equation are the spin sums when you're doing cross-section calculations. You will see that you will be required. So suppose you have 2 beams of, say, fermions coming, and then scattering and going away. Often what happens is that in experiments, the incoming beams are not polarized. And then when they scatter, the detectors are usually not sensitive to spin. So a lot of times, when you're computing amplitudes, you will have to average over the initial spin of the particle and sum over the final states. It actually makes life easier. Your amplitudes look a lot more simple that way. So in those cases, and also in calculations, the spin sums become very useful. And the spin sum is basically a statement about the completeness of the U's and V's. So see here, I am actually taking an outer product of U and U bar. So U is a column matrix. What is U bar? Come on?
Row.
It's a row matrix. So this thing is actually a 4 by 4 matrix. And we are summing over, there is no sum over P. We are summing over the spins. Then we should get P slash minus M. I think there's a typo here in the lecture notes. I wrote plus sign there, but it should be minus. And similarly, for the U's, so the V's, sorry, we get a plus sign here. I think those signs got flipped in the notes. All right, so what we have constructed here are momentum eigenstates, the positive frequency momentum eigenstates, and the negative frequency momentum eigenstates. The Dirac equation is a linear equation. Therefore, any linear combination of these guys will also be a solution to the Dirac equation. So the most general solution to the Dirac equation we can write as no longer a momentum eigenstate, e cubed p 2 pi cubed 2 ep. You guys should know that this measure is Lorentz invariant. Six out of 10 times this question will be asked in the interview to show that this is Lorentz invariant. And when you can't do that, that's a bad sign, okay? And we sum over all the spin states, the spin labels, and they're the U spinners. And then we use a coefficient, it's a Fourier coefficient. And then we add to that the V spinners. And because the Dirac spinner is not real, the coefficients don't have to be complex conjugate of each other. So we write it as C star. Okay? And similarly, for psi bar, we have the same things. And except here we have U bar of S of P. Here we have B star of S of P E plus I P dot X plus V bar of S of P C S of P E to the minus P dot X. Just the, might as well write this. Right? So this is our solution to the Dirac equation. So for the rest of this class, we're going to study the continuous and discrete symmetries of the Dirac-Lagrangian. We may not get to the discrete part given time constraint, but if that happens, we'll treat that next time. However, today's tutorial will be about discrete transformation. We will study very closely P and C, okay? Parity and the charge conjugation. We won't have time for time reversal. And the other thing that we do want to get into today is how to quantize the Dirac field. So before we go and discuss about the continuous and discrete symmetries of the Dirac-Lagrangian, let me remind you of Noether's theorem. Suppose you have a set of fields, phi A, in your theory, and you make some transformation of the fields, or the transformation of the fields can result from some underlying transformation of your space-time manifold, or it could be a combination of both. And the transformation has to be continuous and global. So global, meaning that the parameters of the transformation cannot depend on space-time points. And global and continuous. So let's take an infinitesimal. Decimal transformation. And suppose that our field changes in this way. Okay. And it may leave our Lagrangian invariant, or it may change the Lagrangian up to some total divergence term, where f is something that vanishes at spatial infinity and also at infinite past and infinite future. If this happens, then our action is invariant under this transformation. The action doesn't change. Then Noether's theorem tells us that there exists a current, which is given by this formula. You sum over all the fields. For all the fields, you sum over this thing. The derivative of the Lagrangian with respect to the derivatives of the fields times x of A of phi minus f mu of phi. And that these currents are conserved. That's what Noether's theorem tells us, that using the equation of motion, you can show. Now, if you take this current and you integrate it over all space, And then you get a charge. Sorry, if you take the 0th component of the current and integrate it over all space, then you get something which we call a charge. And then this equation implies that the charge is a constant of motion. That charge is conserved. So this is Noether's theorem. You have seen this in Dan's part of the class. Now, I'm going to erase that. Sorry. And now we are going to have a little bit of a exercise. So let's look at the global phase symmetry of the Dirac-Lagrangian. So let me remind you, the Dirac-Lagrangian then it should be obvious that psi going to e to the power I of alpha of psi and psi bar going to e to the power minus I alpha of psi bar is a symmetry of this Lagrangian. Now let me give you a few minutes, say 3 to 5 minutes. Can you find out what is the conserved charge for this symmetry? So talk to your neighbors and figure out what this is. Okay? The formulae are given there. The first thing you want to do is to work out what this is and what this is.
Corresponding to this one plus, again, this term times d5 corresponding to that one. That's what I think. As in, I need this, this.
Right? Let's take one more minute.
Yeah, this is only at points.
Yeah, because it coordinate
So you cannot find the equation.
Okay. Do we have any volunteers? Volunteers?
Am I will?
Anyone wants to volunteer the answer?
Sidebar. Side.
Sorry?
Sidebar.
Oh, it's the rest of it.
Psi bar,
It's yeah.
gamma, mu, psi. Very nice. So how does it follow? So if you take the infinitesimal transformations, then you get I alpha of psi, and here you get minus I alpha of psi. And then our formula says that J mu.
Isn't that one psi bar?
Yeah. So, so our formula says that we have to take the derivative. You can think of it as taking the derivative with respect to the component. So this guy is the first, the xa, and then we have another term, and there's a minus sign coming from the minus I here. It's a psi bar. And but it turns out that this is 0 because the Dirac-Lagrangian doesn't have a derivative of psi bar. And so this becomes, I think there's a plus I and there's a plus, so there should be a minus sign, right? It's a minus sign of psi bar, gamma mu of psi, and there's some arbitrary constant, so this is the result. And if you look at the 0th component of this thing, this is a positive definite quantity as long as these are not operators. When they're operators, they actually don't become, they change their character. And because it's a positive definite quantity, that's why Dirac wanted to have a first order Lagrangian, because he wanted to interpret this as probability density. But a better interpretation of this is a charge density, as we shall see later today. All right. So what other symmetries, cool symmetries, I should say, does the Dirac-Lagrangian have? So in the limit, where the mass term goes to 0, the Dirac-Lagrangian has this symmetry. It's called a chiral symmetry. And this implies that psi bar transforms in this way. This is also a good interview question. One of the often made mistakes is that people put a minus sign here. Figure out why there's a minus sign. You should work this out. So that's a symmetry of the kinetic term, and so it's only a symmetry of the Dirac-Lagrangian in the limit where the mass is 0. And then we have translational symmetry. So if you translate your space-time, then Noether's theorem gives you a set of 4 conserved currents, because there are 4 transformations here. So you have 4 conserved currents. So it actually becomes a tensor. And these are the conserved currents. If you take the 0th component of each of these conserved current and integrate them over all space-time, you get a 4 vector, which is known as the energy momentum 4 vector. So this is what is known as the energy momentum stress tensor. And this is the energy momentum 4 vector. The 0th component of the energy momentum stress of the 4 vector is what we call the Hamiltonian. And I think in the notes there, I put an I there by mistake. So the Hamiltonian is this thing. And lastly, but not least, we have the Lorentz symmetry. And these 2 symmetries together give you the Poincare symmetry. And the Lorentz boost leads to, and the rotation leads to 6 conserved charges, 6 independent conserved charges, 3 for the rotation, 3 for the boosts. And these are given by it's a rather involved expression. I think there's a gamma 0, yeah. So the ij component of these guys are the angular momenta, is the angular momentum, and see that there are 2 things that contribute to the angular momentum. This part is the spin contribution to the total angular momentum of the field, and this part is the orbital angular momentum contribution to the total angular momentum of the field. Okay? And the 0I part of these conserved charges, they refer to the conservation of the center of mass of the field. So we can now move on to quantization. The quantization of the Dirac field So here we are going to appeal to the spin statistic theorem. Remember, I told you that the spin statistics theorem tells us that fermions correspond to spin half representation of the Lorentz group. Do you have a question?
Yeah, going back a bit.
Yeah?
So I know right now we're still classical, but I remember during one of Dan's lectures, he mentioned that Noether's theorem wouldn't always hold once we quantize everything. Was the axial chiral symmetry, was that?
That's one of those symmetries which are which turns out to be anomalous.
Why?
So, well, there are different ways of looking at it. One is you can show that. I think it's easier probably in the path integral context. Is that you can show that the measure, the path integral measure, that you that's actually not invariant under the chiral symmetry, and in the more canonical context, you actually have to do you actually have to do when you do the renormalization, you can show that that the symmetry is broken by the loop effects. There is nothing wrong with having an anomaly because the quantum theory is the real theory. So having an anomaly it's almost like a misnomer because you're saying it's an anomaly as if there's something wrong with it, right? It's not. It's just like, it's there in the quantum theory. The problem with when a gauge symmetry, as we'll meet gauge symmetry in the context of electromagnetism. It's when a gauge symmetry becomes anomalous, that's when it's a problem. That actually tells you that it's actually an inconsistency of the theory. But so far, we are dealing with global symmetry. There's no problem of this symmetry becoming anomalous, unless, of course, it violates some theorem like CPT theorem or something like this. So yeah, you can think of it as a path integral measure not being invariant under this, or that it's loop effects. So yeah, it's not very insightful, but it's a mathematical kind of. But anomalies are fun. I mean, I think in QFT3, Dan will actually do some anomalies. So, okay. So the spin statistic theorem tells us that we should use anti-commutators to quantize the Dirac field. You can try to impose a commutation relationship on the Dirac field if you want to, but the bad things will happen if you do. For example, if you try to quantize using, say, commutator, then the Hamiltonian is unbounded, becomes unbounded from below. So we better quantize using anti-commutator. Now, in the non-relativistic setting, if you impose the stability of the Hamiltonian, it actually leads to the spin statistics connection. Meaning that in the non-relativistic setting, if you impose the stability of the Hamiltonian, then fermions are described by fermions are in the half-integer representation of the rotation group, and bosons are in the integer representation of the rotation group. Okay. Which is something nice because you don't expect, say, like in a condensed matter system, which has 3 spatial dimensions but is not relativistic, you expect the fermions to be in the half-integer representation of the rotation group there, and the bosons being in the integer representation of the rotation group there. So the spin statistics connection is there if you impose the stability of the Hamiltonian. Whereas in the relativistic setting, the spin statistics connection is a it's a necessary condition for the Hamiltonian to be unbounded. So, as a prelude to quantization, we can take the expression for psi and psi bar and set the time variable t to 0. And why are we doing that? We're doing that because once we quantize, we would like our operator to be in the Schrodinger picture. So we set in psi dagger t equals to 0. The momenta conjugate to psi a, so the momenta conjugate to psi a is defined by this. And if you plug in what the expression for the Lagrangian is, this is what you get. So then our anti-commutation relationship that we impose is and let me just for the moment reinstate H bar. If I now plug in the expression for pi, then this factor of I cancels out. And let's set H bar to 1. So this is our non-trivial anti-commutation relationship. We also impose that psi A anti-commutes with another psi B, another psi phi. And psi dagger of A anti-commutes with another psi dagger. All right? Yeah?
What is the index? The sub-index here?
A is a spinor index.
Oh.
This is a spinor index. So if we now translate these anti-commutation relationship in Fourier space, then the modes have to satisfy these anti-commutation relationships. Yeah.
What do you mean by this spinor index? I mean, it runs from like 1 to 4? Or?
Yes.
Okay.
Yes. 1 to 4. And all the others vanishing. All other anti-commutators vanishing. So, for example, the anti-commutator between B and C dagger, B dagger and C dagger, C dagger, those all will vanish. Yeah.
Wouldn't it make more sense to define these anti-commuting things in terms of Dirac conjugates rather than these?
No. Oh, you mean this?
Yeah. And
You can, but it's yeah, you can do that, but you just multiply by 4x4 matrix, and then you will have, some people have done that, and you will have a gamma gamma 0 on the right hand side in that case. You can do that.
One more fundamental than the other, or
Sorry?
is one more fundamental than the other?
No. So what is fundamental, I think, is the anti-commutator between the field variable and its momentum conjugate, and everything else just follows from that. Okay? Because this came from this guy, but plugging in this definition of pi. Okay, let's do a sample calculation to get the feel of these guys. And the calculation that we're going to do is that starting from these relationships, we shall verify that this holds. And you should always do one of these calculations, a few of these calculations, sometime in your life. And you'll realize that they're straightforward and slightly boring, but sometimes they contain surprises. All right, what is the computation we want to do? We want to start with this. And then what we want to do is that we want to expand the field and its Hermitian conjugate in Fourier space. So we have d cubed of p1, d cubed of p2. There is 2 pi to the power 6, 2e p1, 2e p2. And there are two sums, spin sums, coming from psi and psi dagger. And let's write the spinners. The spinners, us of p1, there's an a here. U dagger r of p2, there's a b here. And then there would be an anti-commutator between bs of p1 and br dagger of p2. Then the exponential is, I think, the first one. So I 3 vector p1 x minus I p vector 2 p2. These are 3 vectors. And then we have another term, which is now v of s of p1 and v of r of p2. And there's a dagger on this one. And then there's a cs dagger of p1. I think I mixed up the dagger and between this guy and that guy in the notes, but it kind of doesn't matter because we'll see some delta functions set all their arguments to the same. So CR of P2 and then e to the power minus I P1 dot x plus I P2 dot y. Okay. So this is, and there will be the other commutators, the commutators between the B's and C's, I've set them to 0 already. So I'm not going to write out those terms. And then this measure remains the same. The sum remains the same. That U of S, P1 of A, these guys remain the same. But then we replace this by, we use the anti-commutation relationships. So we get 2 pi cubed 2 of EP delta of SR delta 3 of P1 minus P2 e to the power I P1 dot x minus I P2 dot y. And then over here we have the v's remain the same. I forgot A and B here. P1A, V dagger, R, P2B, and then we have 2 pi cubed 2 EP delta SR delta cubed of P1 minus P2 e to the power minus I P1 dot X plus I P2 dot Y. Whew. Yeah, my alignment got unaligned there, went out of alignment. All right, so we have now momentum delta functions here and here. So using these delta functions, we can do one of these momentum integrals. That'll set all the P1s and P2s to be the same, say P1. We can also do one of these spin sums, and using Kronecker deltas here and here, that will set these spin labels to be the same. So after you have done that, you can see that you can use the fact that gamma 0 squares to 1 to introduce some gammas there. And then you can use the completeness relationship for the spinners so this is our completeness relationship. And similarly for the V's, to rewrite this in the following form. So we are rewriting using the completeness relationships. We get. So we only have one momentum integral left and one of these guys, and then so use the first term gives us gamma 0 P0 minus gamma I Pi plus M. Should it be plus M or minus M? It should probably be minus M. I think it should be minus M, but okay. And there's AB, or you know, like we'll just take AB of the whole thing. E to the power I P dot X minus Y, and then the second term is then gamma 0 P0 plus gamma I Pi plus M. Gamma 0 e to the power minus I 3 vector P X minus Y. Now what we do is that in the second term we take Pi to minus Pi. Okay? And our integral measure is invariant under this exchange. Okay? Because there are 3 integration with respect to P, so you pick up one minus sign there, and then you reverse the integral measure from minus infinity to plus infinity, from plus infinity to minus infinity, back to minus to plus infinity. So you get 3 minus signs there. So in the end, you get 4 minus signs, okay? Or even number. So this is invariant under this, the measure. As a result, this thing flips sign in the second integral, right? So this thing flips sign, and therefore this term these terms cancel out. This also flips sign. Okay, they should be. I made some mistake here. Because those two things should cancel out. Oh yeah, sorry, yeah. The original. Okay, so yeah, sorry. The original thing should have this minus sign. The sign should only be different here. Sorry, I wrote the wrong sign here. So when you take pi to minus p, because if you look at the completeness relationships, it's this sign that is different. So when you take pi to minus pi, this sign from minus becomes plus, and therefore this will cancel this. So as a result, we have d cubed of p 2 pi cubed 2 EP, and then here we have 2 P0, because the the gamma zeros square to 1, and we have a delta AB from the fact that gamma. So what we are doing here is this, what's left of the gamma matrices of the spinor indices are just basically 2 gamma zeros, and they square to 1. And we are looking at their at the alpha beta element of that identity matrix. And then we have e to the power plus I p dot x minus y. And so these two things cancel out. And then we have delta of AB and e to the power I, and the integral of the exponential gives you a delta function, a direct delta. Okay? So I should probably also write here AB to kind of point out to the fact that we are taking the AB element, the spinor AB element of this whole thing. Okay. So it turns out that we have confirmed that the anti-commutation relationships between the position space and the momentum space are consistent. Now, in the classical limit, we take h bar to 0. Then our anti-commutation relationship, which was non-trivial, become this. And that's what, in the classical limit, this should be a Grassmann variable. Okay, so this and psi dagger should be Grassmann variable. Okay, let's confirm that this quantization procedure has actually given us Fermi-Dirac statistics. So we want to confirm we have Fermi-Dirac statistics. It should follow from the anti-commutation relationship. All right. So let's look at the one particle states. Then a particle with momentum k, 3 momentum k, and spin s is given by so we define the vacuum to be the state which is annihilated by all the B operators and annihilated by all the C operators. So that's how we define the vacuum. And if we apply the dagger operators, which we will see will have the interpretation of creation operator, we get a state, we should have a K here, a one particle state. And the antiparticle state, we shall see, is given by applying by the C operator on the vacuum. The interpretation of this being a one particle state and this being an one antiparticle state will come when we write to the charge operator explicitly. So that's number one. So we have to look at the two particle state. So in the two particle state, we create, say, suppose we take two particles, like instead of, we can take two antiparticles or two particles. Let's take two particles. Right. But remember that these guys anti-commute. So by using the anti-commutation relationship, we can create the state where the labels of the particles are interchanged. But there's a minus sign coming from the anti-commutation relationship. And therefore, we see that indeed Fermi statistics is implemented in our quantum theory. Let's write down the expression of the Hamiltonian in terms of the mode operators. The Hamiltonian can be defined as the Legendre transformation of the Lagrangian. And you can show that this is notice that if psi I were not anti-Hermitian matrices, or that it would be very hard. If it didn't have clearly well-defined hermicity or anti-hermicity properties, it would be very hard to define a Hamiltonian which would be Hermitian. Given the definition, given the fact that psi I are anti-Hermitian, you can show that this Hamiltonian is actually a Hermitian operator. Now, if you express the this Hamiltonian in terms of the mode operators, so you express psi and psi bar in terms of its mode expansion and use anti-commutators, then you can find, and I encourage you to do this calculation. I did it at some point. The expression for the free Hamiltonian is formally infinite because of this term. It reflects the volume of the momentum space. And what you should notice is that the sign that you get for the 0-point energy is opposite of what you would have gotten, you got for the scalar part. And this is related to the fact that in supersymmetric theories, the 0-point energy is all automatically 0. So to get rid of the 0-point energy, we normal order the Hamiltonian. However, because we're dealing with fermions, the normal ordering will involve a subtlety. It turns out the normal ordering for fermions involve a minus sign. So suppose we want to normal order two operators, one annihilation operator, one creation operator. Then inside the normal ordering, we can switch them around, but unlike the bosonic case, we have to actually use a minus sign. And once we have normal ordered, taking into account the minus sign, we can take the normal ordering sign out. So if you normal order your Hamiltonian in similar way, okay, so if you start here, then you will not have it gets rid of the 0-point energy. So this is the expression for the normal ordered Hamiltonian, and you can see that it consists of two number operators, the B number operator and the C number operator. That means that the B's create one type of particles and the C daggers create another type of particles. It doesn't tell you that one is the antiparticle of another, but it tells you there are two kinds of particles in your theory, okay? And they each carry the same amount of energy, right? So to see that one is an antiparticle of the other, let me tell you what the expression of the charge operator is. Again, it's an analogous calculation, maybe a page or so. Unfortunately, I don't have time to do this here. You already look very bored, so I don't even want to bore you more. But you should do that calculation yourself. And you find that the normal ordered expression for the charge operator has first the number operator. And there's a minus sign. So the charge operator is a very simple, consists of two number operators, but the B type of particles contribute with positive sign, and the C type of particles contribute with negative sign. And that's the interpretation that the B type of particles should be interpreted as particles, and the C type of particles should be interpreted as antiparticles. So this sign is a antiparticle interpretation of C's, of C dagger. Okay? So let's now write our field operator, but in the Heisenberg picture. So this is our field operator in the Heisenberg picture, and it's related to the one in Schrodinger picture by the usual unitary relation. And what it does is it keeps it mostly the but it adds this new time dependence part, which is just a phase. And Bs of p, c dagger, but these are now operators, so I'm going to use dagger here. Here it's plus I EP of t minus I p dot x. Okay? So this is our expression for the field operator in the Heisenberg picture. So remember that, yes?
You had a problem in that normal ordering. I think the minus sign is flipped.
Sorry?
The minus sign from the second to the third part in the normal ordering of the Hamiltonian. I think there should be a minus in the left-hand side.
Yeah, sorry. Thank you very much. Yeah. Oops. Sorry. Thank you. So remember that I promised you an infinite dimensional unitary representation of the Lorentz group. These particles, one particle, two particle, multi-particle states, they form that infinite dimensional unitary representation of the Lorentz group. So what do I mean by that? I think so for example, if you apply B dagger on the vacuum, you get a one particle state, but you can apply any number of, say, B's and C's on it, and as long as their arguments are not the same, they will give you multi-particle states. And you can apply the Hamiltonian on these states. If you apply Hamiltonian on these states, say B of R of P, it's an elementary calculation that you will find that they are eigenstates of the Hamiltonian with the same state. So these states, they form an infinite dimensional Hilbert space. This is also sometimes called the Fock space. And that is the, I don't have time today, but I was going to give an exercise that, assuming this is equal to 1, it's an easy exercise to show that the inner product between two states, just by using the anti-commutation relationship, is something positive okay? And therefore, it's unitary. This representation is unitary. Okay? You can try to show its unitary in another way. So you can now construct the unitary operator which implement the Lorentz transformation, and they will have the form e to the power minus I by 2 omega mu nu. And remember the conserved charges that we derived, or I mentioned as a result of the Lorentz transformation. If you compute this, you can show that this is a unitary operator. So for this, I haven't done this particular calculation, but I have done other analogous calculation. But you have to express this J now in terms of the mode operators, and you should be able to derive, or in some other way, that this is actually a unitary operator. Okay? So in the last 10 minutes, let me just touch upon discrete transformation. We will have more to say about that in today's tutorial. So when we defined, So let's start with charge conjugation. Remember, when we defined our Majorana spinner, we defined the charge conjugation acting on a spinner in this way. I didn't really motivate why that was so. A way to motivate this is to kind of write down what the Dirac equation is in the presence of an electromagnetic field. We will see in the future that this is the form that the Dirac equation takes in the presence of an electromagnetic field. You also may have seen some analogous relationship involved, where A mu is the 4-vector potential of E and M. The Schrodinger equation also has this an analogous form. So you can show that but by just taking the complex conjugate of this, that the charge conjugate spinner satisfies, it also satisfies the Dirac equation, but with a plus sign here in front of the charge. Where gamma hat mu is related to the gamma mu by this, but you can show that gamma hat mu also satisfied the Dirac equation. So if you look at these two equations, they're both Dirac equations, but with E replaced by minus E. This motivates why we define charge conjugation in this way. In terms of mode operators, you expect the charge conjugation operator, which, by the way, since it's a conjugation operator, should give you 1 upon squaring. That means that C inverse is equals to C dagger. It's unitary, but that's equals to C. So the charge conjugation operator on mode operators should take the creation operator for a particle to an a creation operator of an antiparticle. So these guys are now operators, so other operators act on them by conjugation, or by, similarity transformation. And that should give us, we will show in today's tutorial, or we shall try to show in today's tutorial, that these relationships actually imply, through the properties of the spinner, this transformation. The last thing I wanted to mention is parity, or maybe the second last thing. So parity should invert the momentum dependence of the creation operator. So a parity operator acting on, say, B, on the creation or annihilation operator should just simply give us this, where it's a 3 momentum. However, both in the charge conjugation case and also in the case of parity, there's room for a phase factor here, eta of B. And I'll explain why. So CS should give us eta C of CS of minus P. And the reason is right. See, spinners are like all the observables that we can make out of spinors are bilinear in spinors and their conjugate. So the observable are bilinears in, say, psi and psi bar, or I should say psi bar and psi. So if we will see that in today's tutorial that these phase factors, which in this case is called an intrinsic parity, so they can, hang on. Sorry. Right, yeah. So the fact is, when you apply the parity operator twice, you should get the identity operator, but because our observables are bilinear in psi and psi bar, you actually don't have to get, when you get eta squares to where eta square equals to 1, you can have actually eta square equal to -1. Because in the observables, if you apply parity twice, then you would pick up 2 minus signs if you were to choose eta squares equal to -1, and then your observable would remain invariant under parity. Okay? So we'll see in today's tutorial that for the Dirac field, the parity, that the consistent choice that we have to make is that the intrinsic parity of the particle has to be related to the intrinsic parity of the antiparticle in this way. What does it mean to say that a theory is invariant under a discrete transformation, such as parity? That means that your Hamiltonian operator commutes with P. And I don't think I'll have, I won't have time to talk about time reversal. There's a brief section on time reversal in the notes, so I think I'll stop there. Any questions? So is this clear why this is the case? Sorry, I kind of didn't. I kind of stumbled a little bit on that argument. Is that so? If you apply P twice, you should get you should get like 1, right? So you should get 2 factors of eta here. But eta doesn't have to be 1. It can be -1 because, when you have some observable like this, there will be 2 etas. There'll be a -1 coming from the mode operators in this one. There'll be a minus sign coming from this mode operator from this one, and therefore it'll give you it'll remain invariant. Okay. All right. If there are no questions, I'll see you guys at 2. in the tutorial.